So previously, we looked at a number of concepts under conic sections. And we saw the basic structures for conic sections. We did look at the ellipse, the circle, the hyperbola, and the parabola. But this time around, we want to look at the same conic sections, but want to look at more descriptions and more treatments about the same conic sections. And we want to finish it off completely. So generally, I did point out in last night's class to say that these conic sections will have a general formula where you have some number, real number a, and then x to the power 2, and then we're going to have bxy, and then you're going to have cy squared, then you have plus dx, then you have plus ey, and then plus f is equals to 0. Here, of course, a, b, c, d up to f, these are real numbers. It can be any real number. Now, what we're trying to say is that any conic section that you're going to be given can be represented in this form. And we saw from last night's class to say that when you are given a conic section which is in this form, it is actually possible for you to transform it so that it takes that form or the standard form of either a circle, parabola, hyperbola, or an ellipse. But of course, most of those will not have this term, which we are calling the cross product. So most of those conic sections that we did last night did not have that term containing both x and y. So that was the cross product. Now, what if you actually have a cross product present, as in you have a term in the expression which actually has that cross product? What would be the treatment there? Well, firstly, if you had such an expression, let's say you were dealing with, we can start with, let's say you're dealing with an ellipse, for example. So, to say an ellipse, if it is something that, an ellipse that, whose measure is in the x-axis, to say you'd have an ellipse that is more like this. So this is an ellipse, measure x-axis, and this ellipse is obviously centered at the origin, or at least that's what I'm trying to go for. But if this ellipse was maybe not necessarily flat out like this, what if it was a little bit rotated? Something like, maybe we can even bring it up to somewhere there. Well, it turns out that if this ellipse is now in this form, it will be a little bit difficult to present it. Its expression will now have this cross product being present, as in if you try to expand its equation, you'd end up with the cross product being present. But the cross product is a little bit difficult to work with, because all the other conic sections, the hyperbola, the parabola, and basically those three, hyperbola, parabola, and the ellipse, when they are rotated a little bit about some common point, you find that now the cross product is going to be present. Now, if the cross product is present, when trying to complete the square, you're going to have a challenge. Where are you going to associate that term containing both x and y? Are you going to group it with the term with an x here? Or are you going to say that you group it with the term that has y here? Where are you going to associate it? Well, in this case, it's a little bit tricky. So to avoid this part, we use a trick. We just translate the axis so that instead of looking at it like that, we now consider it about a new x-axis, and this new x-axis will run in that manner. So this is how the rotation of axis works. So you now consider the same ellipse, but about this new x-axis, and you take this as the x prime axis. Or I'll use x like that to mean the new axis, and I'll use x like this to mean the old axis. And about the y-axis now goes somewhere there. So ideally, we're saying that these are still perpendicular to each other. So I'll say this is y like that, and I'll use this to mean the old y. Okay, now the question is, how are these related? Okay. Now, for a case like this, where the x-axis has been rotated through some angle, let's say the angle of rotation here is, let's say, theta, from the original x-axis here to the new x-axis here, somewhere there, it has been rotated through some angle theta. Notice that even this side, the y-axis would have been rotated through the same angle theta. Now, how do we relate the coordinates or the variable x from the old one to the new one? How can we relate them? We won't do the derivations here, but instead, we'll just show you how they relate. Well, it turns out that a point which was initially given, let's say, when you try to locate, let's pick a few points here. We can pick, let's say, a point that is here. If you picked that point about the x-axis, the original x-axis, what you'd have is that you'd have x, the y-axis or the y-coordinate going somewhere there, and the x-coordinate coming down somewhere this side. Now, this is if you looked at it in the old coordinate system. But what if you looked at it in the new coordinate system? Well, in the new coordinate system, now what you'd have to consider would be the y-coordinate or the x-coordinate would have to be something like this, something here, and the new y-coordinate or the new y variable now have to be somewhere here. So we see that everything now is being changed. So if we consider the variable here in the old to be a y like that, and in the new to be a y like this, and the x coordinate in the old to be an x like this, and in the new to be an x like that, how are they connected? Well, it turns out that you're going to have a basic connection. The old x coordinate of any point will relate to the new in this form. So you have x here, then you'll have cos, the angle through which the axis is being rotated, then minus the new y, and then sine that same angle theta. In the same way, if you wanted to relate the old y to the new coordinates, you'd have x here, but when you're dealing with y, this is now going to be sine theta, and the sign on the middle is going to be plus. And then you're going to have the new y, and then this is going to be cos theta. So this is if you're changing, if you know, let's say the the new variables, let's say you want to change, it depends with what you're really trying to achieve. If I wanted to eliminate the old variables so that I plug or I end up with the new ones, the x new and the y new, I'd have to make this substitution wherever there is x there. Okay, but if let's say I was given the translated axis, and then I want to know the old, I want to eliminate the translated, how it would look like now, you'd have the new one being subject so that we predict what the old would be. If I wanted to write an expression for the new, what I'd have, it's something similar, but what would change is going to be the sign on the middle. I'm just showing you how best to remember these as you prepare for your exams. So this is going to be the old x. You still have cos. Notice that it's just this equation I'm writing, but the difference is instead of minus here, this will now have a plus. Then again, this is the old y, and you still have sine theta. And we're now writing for the new y. Again, it's the same expression, but now we're writing this one. And the difference here is that when you look at it, this term, the one with sign, the one with sign now is going to be minus. So what you can just pick here is that the sign term changes signs. If it was negative, it becomes positive. If it was positive, it becomes negative. In the first part, it was negative, it has become positive. And now the sign term there was positive. Now it becomes minus. So here we're dealing with x. Then we have sine theta. This is still plus, then you have y, cos theta. So this is what you're dealing with in this case. Okay, any questions here? Okay, looks like we're
down x and y, the rotated axis or the normal axis?
this is for the rotated x-axis. and y. I am using x to mean like this to mean the rotated ones. And I am using this to mean the normal ones. So it's like this is x and y. While this I'm using this y and that x. You get it now?
Yes.
Okay. Okay, so with that in mind, here are a few key tools that you just need to keep in mind when working with these. When you're trying to find an angle, let's say you have an expression like this one. If you have an expression like this one, and you wanted to predict what the angle of rotation so that the cross product gets to be eliminated. The whole idea here is that when this rotation is made, you now have the major axis lying either along the x-axis, the new x-axis, or along the new y-axis. In most cases, will go along the new x-axis. That is what you're trying to achieve. So if you had a conic section, which is given by this expression, how much do you have to rotate it so that the cross product here gets to be eliminated? Well, to predict how much you have to rotate it, all you have to do is use cot 2 theta is equal to A minus C over B. Of course, you guys have seen how this expression is derived, so you can still derive it, but we'll just try to see how to use it. So in this expression, theta here is the angle through which we have to rotate the axis so that the cross product here disappears or becomes 0. Now, of course, knowing the relationship between cot and tan, you should also see that if you had cot 2 theta being equals to this, you can also say tan 2 theta is equals to B over A minus C. So either expression can be used, but depending with what you have, what you're given, it might be convenient for you to use the one with cot instead with the one with sine. Especially in an event where A minus C gives you 0. You might prefer to use this, but even the one with tan can still work there. Just have to know how to spin it. Okay, so do you have any questions there? Let's try to find an example that we can work out using this expression. So what you're trying to do is we want to identify the conic section, and perhaps we also want to sketch it if we can. But ideally, first what I want us to do is, can we try to rotate it so that we eliminate the cross product? Once we rotate it, we'll see exactly what we have, and now try to use completing the square so that we get to have the exact conic section that we're dealing with. So for our example, let me pick something that looks a little bit basic. So let's have an example. Let's say, okay. So perhaps we start a little bit slow instead of jumping into something that is quite fast. Let's start with something simple. So let's say we have an x-axis being rotated through an angle of 60 degrees. And then we want to find, can you find what the x and y coordinates would be? So you have, if the x-axis or not the x-axis, the axis are rotated through 60 degrees, can you find the x and y coordinates of a point whose x, y or xy coordinates are 2, 6. So I'll leave this one for you guys because I feel this is a little bit straightforward. You're given the angle through which you're rotating this, and they're being given what the points are in the odd coordinate axis, and then what they want you to find is what that coordinate would be in the new or in the rotated frame, in the rotated axis. So can you try to work out that, and let's see what you will find there. So of course, you know to say, since you're going for the new, in the new coordinate system, you're basically just going to use this version. It will take you directly. Where there's x, you put the x coordinate, y put the y coordinate, where there's theta, you put the angle. But let's look at the second example. In the second example now, we want to do something that actually does add up. And in this case, let's use xy minus y squared minus 5y plus 1 is equals to 0. Now, in this case, how do we work out this question so that we get to find, actually find what it is? How do we rotate the axis so that we eliminate the cross product, transform the equation so that it no longer has the cross product, and then rewrite it so that we get the exact expression of the conic section so that we are able to know which one it is? Well, the first thing that you need to do is find the angle through which it is being rotated. To find the angle, how do you do it? Well, to find the angle, like I wrote earlier on, you need to work out cot 2 theta is equals to, remember what we had? It was A minus C over B. I hope you guys remember that. Yes, that is A minus C over B. So in this case, what is our A? We know that the general expression is ax squared plus bx, not bxy, plus cy squared. Those are the three that we're interested in here. We see that x squared does not show up here, so A has to be 0. So we're looking at 0 here, minus C does appear. C, that's not C. C is the one with y squared. Y squared is here. We see that C there is minus 1. So I have minus 1 there. And then over B. B does show up. B is the coefficient of the cross product, which is just 1 there. So we have, this is basically just 1 here. So it's 1 over 1, because that is minus 1 will make that a positive. So we had cot 2 theta is equals to 1. Now the question is, what has to be theta if this has to be equals to 1? What do you guys think? We start with what has to be 2 theta if the answer here has to be 1. Can you see that? Because here we're saying this is here 90, 45. Which one is it? Okay.
I was saying for 2 theta. I don't know, maybe he was just saying for theta.
Okay. So all you know here is this. Firstly, you know that tan 45 is equals to 1. Right? So tan 45 is equals to 1. So it implies that if you have 1 over tan 45, which is basically just cot 2 theta, this has to be equals to 1 as well. So in other words, not that, this is 45. So what this implies is that the 2 theta here must be this. Well, let me not relate it from here. The 2 theta must be that. Do you get that? Do you agree with this?
Yes.
Yeah. So the 2 theta here has to be, okay, so someone is asking us to go through that one more time. So the concept here is quite simple. We know to say, I can even look at it from the other expression. The other expression was tan 2 theta is equal to B over A minus C. We know A is 0, B is 1, C is -1. So you have 0 minus -1. so that this ends up being equals to 1. So now seeing tan 2 theta is equals to 1. So how does it work in this case? Want to know what the angle this must be so that tan whatever this angle is going to give us 1. We can actually even redefine this angle and say this is phi, and say phi is equals to 2 theta. So that now we look at it as tan phi is equals to 1. Now the question is, what must be phi if tan phi has to be 1? We know to say, moving from 0 to 360, tan will give you 1, even let's say from 0 to 180. Tan will give you 1 at 45. Even from 0 to 360, to get positive 1, it can only be at 45. Tan 45 has to be 1. Because of that, we then go on to claim that phi here has to be equals to 45. But what is phi? Phi is 2 theta. So we then conclude that 2 theta has to be equals to 45, so that theta has to be equals to 45 over 2. And this ends up being 22.5 degrees. So this ends up being our angle. Do you see that? Okay. Well, the last
22.5, is that when we're using tan or when we're using quotes?
Whether you use tan or quote, you still find the same thing. If you use quote, you're looking at quote 2 theta is equals to 1 over 1. I think we did see this part. It's equals to 1 over 1. And what happens here? So this is basically just quote 2 theta is equals to 1. But what is quote? Quote is the same as 1 over tan. So 1 over tan has to be equals to 1. Don't you see that this is just 1 is equals to tan 2 theta? Because we don't know what quote is directly. Or the only way we can know what quote is through tan. So we still end up with just tan 2 theta being equals to 1. So that answer I found using tan, it's still the same answer I would arrive at using quote. So the logic here again would be, what must be this angle? Not just theta there, what must be the whole angle here if tan the angle has to be 1? Now, it can't be 90. It can't be 90. You have to see that, because even if you tried to use tan on your calculator, you'll see that this will not actually come out. It won't give you anything. It won't even give you 1, because tan is the same as what? Tan is the same as sine 90 over cos 90. And cos 90 is 0. So this would give you 1 over 0, which is undefined. Next thing, theta itself cannot be 45. Because if theta is 45, to double it would make it 90, meaning that you'd end up with tan 90 here, which is what we're just from describing. And if we had, or if we say that theta is 90 itself, then it would mean that tan 2 theta would be 2 times 90, which is 180. So you'd be looking at tan 180. And if you tried tan 180, will it give us 1? Let's see. It's sine 180 over cos 180. And what do you get here? Sine 180 is 0. Cos 180 is negative 1. It doesn't give us 1. But if you tried 22.5, if theta was 22.5, it would be 2 multiplying 22.5. Double 22.5, you have tan 45. And tan 45 is 1. Is that okay?
Yes. Yes.
Now, what I would say is this. Perhaps this looks odd to you guys for one simple reason. In all the cases where you actually had to do this, you never got an angle like this one. Why? Because if you get an angle like this one, it would be very difficult for you to simplify the expression. Because the next part would be to use this to simplify this expression here, where here we had cos theta, and then plus, this was minus, I mean, and then this would be sine theta. The concept is that you must then get this angle and plug it here, but you must not remain with sine this or cos that. It must simplify, or this has to be a special angle so that it's easy for you to predict what cos that angle is without using a calculator. This is the reason why when you have to rotate the axis, in most cases, the angles you'd have will be 45, which is a special angle, 30, which is a special angle, 90, 180, and the likes. So these are the questions that you guys probably are used to seeing in this case. Do you agree? Okay, so based on that, let's try to see if we can find a good example that we can use so that we are able to work it out to the very end instead of, so at least at this point, it should give us a special angle. Okay, consider this example. I think this is going to be a better example where we actually are expected to do everything to the very end. So we're going to focus on B there. You can try out A as well. We should be able to work out A, something that we did last night. So consider that example there. So in this case, they're saying rotate the coordinate axis to transform the given equation into one without the cross term product, and identify it. So how do we do that? So just as I showed earlier on, you want to use cot, not cos. So you have cot 2 theta is equal to, you have A minus C over B. Identify your A. A is the coefficient of the x squared term, so which is 1. Identify your B. B is the coefficient of the y squared term, which is 1. And your C, the xy term, the coefficient there, that is the one that comes out as 1. And C is the coefficient of the y squared term, which is also 1. So it's that in this case, we have 1 minus 1 over 1. So that we see that we end up with cot 2 theta is equals to 0. Now, when does cot give us 0? Well, cot is 1 over tan, and 1 over tan is cos 2 theta over sine 2 theta. For this to give us 0, it implies that cos must be 0. So this implies that cos has to be 0. You see, if cos 2 theta is actually equals to 0, then it won't matter what sine 2 theta is, the solution will always be 0. So in this case, our focus now changes to cos there. It's what it will help us figure out what the theta is. So what must be the angle? What must be the argument here if cos this argument has to be 0? Well, if we're looking at from 0 to 360, cos gives us 0 when the angle is 90 degrees and also when the angle is 270 degrees. Did they give us a range to restrict us? They did not. So we'll go with the first one. We'll go with 90. Okay, so cos gives us 0 here and there. So let's go with this one. So in this case, we're implying that, okay, so it means that the argument there, which is 2 theta, must be equals to 90. So if the argument is 90, then this comes out as theta is equals to 45 degrees. So we have found a special angle as our theta. Having found what theta is, we can now transform our equation. It's given in the original frame where we have x and y. So we're now going to transform it. So to transform it, the new is going to be the one that starts first is x. So you have x here. And remember, this is cos 45. But what is cos 45? Cos 45 is equals to 1 over root 2. You can say 1 over root 2 or root 2 over 2. Because of that, where there's cos 45, I'll say 1 over root 2, which is basically just x over root 2. This is minus, and then I have y, and then again I have sine 45. Well, it turns out that sine 45 and cos 45 are the same, 1 over root 2 as well. So at here I have this over root 2. Then when it comes to the odd y, we know to say this has to be x, and then sine 45. Again, sine 45 is still 1 over root 2, so I have this is over root 2. Then this has plus here. Then y over, or y multiplying cos 45. Again, cos 45 is 1 over root 2, so I'll still have this root 2 here. Now that I have the connection, so this is what I was going for. Remember in the previous one that we wrote, we saw that cos 22.2 was not a special angle, so it wouldn't simplify easily. That's why we didn't continue with that. We decided to pick a new example. So having done this, what we'd have to do now is get those expressions and plug them into our equation. What is our equation? X squared plus xy plus y squared is equals to 1. So now get this equation. Where there's x, we'll put the expression for x. So we see that what starts first is x squared. So where there's x squared, we'll put x over root 2 minus y over root 2. But x has to be squared. Then we have plus xy. So x is this. And what is y? When you look at y is the same thing, but it's just plus here. And then plus y squared. So our y squared again is x. Okay, let's put our y squared there. So our y squared is x over root 2 plus y over root 2. Then this is equals to 0. Not equals to 0, equals to 1. So don't forget y is squared there. So now we just have to simplify this and then work out what we have. Notice that where the cross product is, you always end up with the difference of 2 squares there. That is what is going to sort it out. So let's see how it reduces. When I expand this, I try to do this a little bit fast. So that is going to be x squared here. This is going to be over 2. This is going to be minus 2. And then this is going to be x, y over 2 here. The 2 and the 2, of course, will cancel out immediately. Then this will be plus y squared over 2. All this is coming from just the square of this. Then plus, this is the difference of 2 squares. Let me use different colors so that you guys are able to keep track. This is the difference of 2 squares. So how does it expand or simplify? We know to say it's just the first term squared, which will be x squared over 2 because that's root 2 squared. Then minus the second term squared. The second term is y over root 2. So this will be y squared over 2 as well. Then the last part is going to be, is this. So for the last part, what are we going to end up with? So again, I'll expand that. It's going to be plus x will be squared over 2. Then again, these two will multiply. And they'll do it twice. So it's going to be plus 2 xy. But when they multiply down here, this is going to give us root 2. I just have to be careful there. I have x over root 2 multiplying y over root 2. And then plus, okay, yeah, that's I do actually have it right. The 2 sorts them out. So this is going to be over 2 here. And then the last term squared there. So this is going to be y squared over root 2 squared, which is just 2. Then equals to 1. So once we are here, again, these 2 and these 2 will simplify. this term would reduce to what? X squared over 2 plus x, y, and then plus y squared over 2 is equals to 1. On the middle, what we have x squared over 2 minus y squared over 2. This is plus here. Clearly, you can see that this and this will subtract out. Let's continue. We have this is plus, so let me start with this part, x squared over 2. Then we have minus xy. And then we have plus y squared over 2. Then this is a plus. Another thing, this term here and the cross product there dies out. So what we see, sadly, only the 1 y squared cancelled. I thought another x would cancel something, but it did not. Okay, that's fine. So what is left here? We now only have x squared over 2. I'll group them. I think I also have another x squared here over 2. And then what else? Next, I'm seeing y squared over 2. Oh, there's another x squared. There's this one also. This is also x squared over 2. And that was the last one. So I have plus y squared over 2. This one, I think that was the last one there. So this is equals to 1. So these will give me x squared, just x squared. Then this is plus x squared over 2 plus y squared over 2 is equals to 1. From here, these are like terms. When you add them, you get 3x squared over 2 plus y squared over 2 is equals to 1. Look at this. What's the last step here? So that we know exactly what conic section this is. What's the last step there? You have to see that this can be written as x squared over 3 over, not 3 over 2, over 2 over 3. Then we have plus y squared over 2 is equals to 1. This is how it comes out. What conic section is this? Yeah, this is an ellipse. So this is a useful trick that you guys have to remember when you have a number like this coming here. It's the same as just 2 being divided by that number there. Basically the same thing. So be able to remember that. So we have rotated the axis to eliminate the cross product. And the last thing, just as the question was asking, the last part was saying rotate. After that, identify it. We rotated and then we identified it. Having done that, the last part is now about what? Find the foci, the center, the principal axis, and specify the asymptotes, if any. This time we're dealing with an ellipse, so no need to specify the asymptotes. But look at it one more time. What will be the principal axis, the x-axis or the y-axis? So I think the principal axis is the one I usually call the major axis here. What will be the principal axis here? The y-axis. In other words, we're expecting an ellipse that is going to be like this. Okay, so that is done. So y-axis will be our principal axis. And then, of course, having looked at ellipse last night, I trust that you guys know how to get the foci and the center here. And then, of course, I also trust that you know how to sketch it. The only thing we're trying to learn here is how to actually rotate it. Are we okay there? Okay, so we have that question that that was shared also in the group. We are running on a time schedule, on a time wimp, trying to finish everything. But do you guys want me to also spend time working out that, or we move on to another concept? I feel that might review something else that we haven't discussed, but do you want us to do it as well, or we move on to something else? Side.
I think it's more.
Okay. So we'll see if we have enough time at the end to circle back and do it. But it might have been beneficial to actually do it as well. But we'll circle back if we have time. Okay. So the next thing that we now want to look at is going to be when it comes to the test, the discriminant test. Well, you see, you won't manage every time when you're given an expression like what we had earlier on. Every time when you have a conic section represented in this form, you won't manage rotating the coordinate system just for you to identify what conic section you're looking at. This is going to always be very difficult. As you guys might know, not all cases of rotation will simplify like the way the previous one simplified. You might have to actually use triangles here to say, okay, if cot 2 theta is equals to this over that, then and so on. I wanted to show you that as well, but perhaps I'll show you another time. Not all those will simplify like that. Some questions are going to be a little bit more involving, requiring you to use double angle identities, making the problem a little bit too long. Well, the discriminant test gives you a way, an easier way, not of rotating the axis, no, but an easier way of identifying what conic section you're looking at without having to solve anything really. And how does it work? Well, you use the discriminant, and in this case, the discriminant is b squared minus 4ac, where a, b, c represent the coefficient from this expression. Now, how does it work? If the discriminant b squared minus 4ac turns out to be equals to 0, then it implies that whatever the conic section is, whatever this expression is talking about, it is actually talking about a parabola. But if this expression turns out to be anything else, let's say something less than 0. So if it turns out to be less than 0, well, in this case, you are actually dealing with an ellipse. But if instead of this, you are dealing with, or you end up with something greater than 0, it actually now implies that you're dealing with a hyperbola. Now, how does this work? Consider the case or the question that we left midway because we couldn't really, the angle we got was not, it was not a perfect or a special angle. And that was for this expression here. What if you found this question and they are asking you to say, can you identify the conic section? We have seen that rotating the axis here might not really be the easiest thing to do unless if you are allowed to use a calculator so that you can solve cos 22.5 and sin 22.5. But how can we identify it without having to rotate the axis? Well, let's find the discriminant. The discriminant being given by b minus 4ac. When we find this discriminant, in our case, what is our b? Our b here is 1, the coefficient of the cross product. So b is just 1. 1 squared is 1. Minus 4. What is a? A here is 0 because a is the coefficient of x squared. So you have 0. Once you see that 0 here, it doesn't matter what c is because in the end, you still get 0 from this term. So the discriminant here has turned out to give us 1. And what is 1? Well, 1 is greater than 0. Because 1 is greater than 0, it implies that we are dealing with a hyperbola. So our expression is a hyperbola. Okay, so I hope you guys were able to see that. The next thing that we want to look at is the eccentricity. Any questions on the discriminant test before I move on? Eccentricity. Okay, now how does it work? How do we deal with this eccentricity? Well, in this case, eccentricity, just like the discriminant, it's something specific and it describes what conic section we're dealing with. Generally, the eccentricity of whatever conic section that we're looking at is going to be given by E is equals to C over A. Remember what C and A, remember what they are. So you just want to remember exactly what they are. So we saw last time to say that if you're dealing with something like an ellipse or if you're doing something like an ellipse or basically an ellipse, then C here is going to be given, I think what we had was B squared is going to be given by A squared minus C squared. But if you're dealing with a hyperbola, we saw to say that in that case, we had C squared is equals to A squared plus B squared. So just remember these depending on what you're dealing with. But basically, if you're going to find the eccentricity, then this is the formula that you want to use. Now, it's just a number that is associated with each conic section, and it reviews the conic sections type. So if you know the eccentricity, you can actually identify the conic section that you're dealing with. Now, what do I mean? Well, if it turns out that the eccentricity here is actually equal to, let's say, 0, when do you expect the eccentricity to be 0? Well, you expect it to be 0 in an event that, let's say, we had B squared is equals to A squared minus C squared. Flip them around, C goes there, B goes there. You have A squared minus B squared. But if it turned out that A and B were the same, if A and B were the same, notice that C squared would end up being 0. So that if you have now C is 0 over A, this is basically just 0. So if eccentricity is equals to 0, you can even guess what conic section this is. So here, the conic section is going to be an ellipse. Basically, not necessarily an ellipse. It's a circle, but a circle, of course, can be related to an ellipse. Okay, but here, of course, here when we get this to be equals to 0, this we can say this is a circle. So if E is equals to 0, then we're dealing with the circle. But if let's say E is equal to 1, what would this be? Well, for E to be equals to 1, it implies that C here and A here, they must be the same. Now, this, of course, will only come out if you're dealing with a parabola. So if you're dealing with a parabola, then the eccentricity is going to come out as 1. Now, what else? How about if you're dealing with, let's say, a hyperbola? What do you expect E to be if you're dealing with a hyperbola? Can you guess?
Greater than 1.
Yeah. So basically what you have is, if this is greater than 1, then you're dealing with a hyperbola. And if E is less than 1, then you're dealing with an ellipse now. Okay, so this is going to be an ellipse. Are we okay there? Are we okay? Polar coordinates. Well, it turns out that sometimes it might be beneficial for us to represent whatever we're dealing with instead of in terms of the XY plane. It might be beneficial for us to represent a conic section in its polar form. Well, in polar form, we will only be interested in the radius of whatever we're dealing with and the angle through which we are rotating. So those are the only two things that we're going to worry about. But of course, we know the relationship. Consider, you can even say you have an ellipse like this, and then you have something like this. You have a point that is right along the circumference of your ellipse here. So of course, the radius that we have there as r would have to be this, and then the angle would have to be this angle here. And then notice that we can relate the x to r and theta, because you know to say you form a right angle triangle here. So basically all you have is x is equals to r cos theta and y is equals to r sine theta. Then other useful formulas that you might have here is the definition from Pythagoras theorem, x squared plus y squared is equals to r squared, and also tan theta is equal to y over x. So, which is opposite of adjacent. So these expressions are going to be useful when it comes to dealing or changing from either polar to rectangular or from rectangular to polar. Now, how does it happen? Suppose you're given a specific point and they want you to convert them. How would you do them? How would you do that? So let's try to figure out, or let's try to find a specific example for that. So let's say you have, let's have 1, -1. You want to convert this point from rectangular, because this is in terms of x, y. You want to convert this from rectangular to polar, meaning I want to change from x, y to r, theta. How do I do this? Well, since I have x and y, I can easily get r, since I know r squared is equals to x squared plus y squared. So r can be found just by getting the square root of 1 squared plus -1 squared, which just comes out as √2. So r has been figured out, √2. But how do we get theta there? For theta, we saw that we have tan 2 theta is equals to y over x. For y, it's -1. For x, it's 1. So we're basically looking at tan 2 theta being equals to -1. Now, how do we solve this? Tan 2 theta is equals to -1. What has to be the angle for tan? You see, we might not know exactly what the angle might be for us to get -1, but we know at least what the angle must be for the answer to be +1. So we'll target that. What must be the angle? What must be this so that tan gives us +1? We'll start from there. And we saw earlier on to say that this whole thing here must be 45 if tan is going to give us 1. So since that has to be 45, it then implies that 2 theta has to be equals to 45 if tan 2 theta has to give us 1. Wait, how on earth do you end up with tan 2 theta there, guys? Why are you guys not correcting me?
Actually, that was my second question.
Yeah, so I think I'm still hung up on that rotation of axis. So I was at 2 theta here. I was like, wait, where is the 2 theta coming from? I think I did write it earlier and it didn't have 2 theta. It was just theta. Tan theta is equals to y over x there. So this is tan theta. Sorry for that. Sorry for those who got carried away with the 2 theta like I did. So, okay. So the question then is, what has to be theta if tan has to be -1? So like I was saying, the easiest way to approach it is what has to be theta if tan has to give us 1, and we see that theta has to be 45. But now to get -1, we now ask ourselves to say that in what quadrant were we working with? In what quadrant does tan give us a negative? Well, tan gives us a negative in 2 places. So it implies that that 45 we have found, either it is this side in the second quadrant where tan gives us 45, or tan gives us negative, or it is in the third quadrant, or fourth, I mean, where tan also gives us 45, -45. So we'll play with this one. Of course, they haven't specified in this case where our range is, so it can be either. You might want to do both if you have more marks and more time. But in this case, we'll just go with the 45 in the second quadrant. So since I'm going with the 45 there, then the angle can be measured from here all the way up to here. So just less 45 from 180, which gives me 135 degrees. So that now we have our theta, which is 1. So we have our r, which is √2, and our theta, which is 135 degrees. So there we have it. We have made the conversion. Any questions there? So you want to pay attention to, yeah? Well,
would it be wrong if I use the angle as -45?
-45. -45 is also fine. But usually you don't want the negative. The standard way is to measure them anti-clockwise. Negative just means you measure them clockwise. So you might want to not do that. Okay, so that is done. Now, the next thing that you want to just understand here is that how does it work actually? What if you have other expressions that you want to describe? Well, there are a number of things that can actually arise from the expressions that we've dealt with. For example, let's say the ellipse, the hyperbola, the parabola. You see, it can be shown. We won't try to derive these expressions, but by looking at a parabola facing to the right, and then of course centering it at the at one of the at the focus, let's say here, making sure the origin of our coordinate axis was somewhere there. What you can actually end up concluding here is that, sorry, this is then hard to get. Okay, will this work? Okay, this has failed to work. Let me use this. Nice. Okay. Okay, so say we have something like this. This is a parabola whose focus lies at the origin. In this case, we can actually derive an expression and show that we can have our r here, of course, being this distance from here, let's say up to some point here. For a parabola, of course, we know to say we're going to have some directrix that is going to be somewhere this side, some distance, of course, from here up to there. But by doing some math here, we can easily derive the expression and show that the formula for a parabola that opens in this way can actually be represented in the form r is equals to ek over, and then we have 1 minus the eccentricity again, then we have cos theta here. Okay, so wait, this actually has a plus here. The one that opens to the left has a plus here. Okay, Yeah, let me just check through that. Yeah, that is exactly what we have. Now, again, I still want to check through. Oh yeah, that's okay. Now, how does it work here? What are we looking at, and what does this expression really represent? Well, this expression represents a parabola that opens to the left, whose focus is at the origin. Now, what are some of the notations that are given here? E, of course, is the eccentricity. Theta here is just the angle between this and that part. That's not really a problem. But what does the K there represent? Who can tell us what K represents here? What does K represent? You see, in this expression, K represents the distance from here up to where the directrix here is. So in other words, the directrix is a line x is equals to K. So this is what we have in this case. You must really understand what K there gives you. It's the distance from the focus of that parabola to where the directrix is. Once you get what that is, it implies that you can easily sketch this parabola once it is given to you. Now, you can actually use this version to describe anything that you have, be it a hyperbola, be it an ellipse or so. Because if you're dealing with an ellipse, then you can easily look at it as just this, but you just look at it as if that section that is being described there is just one piece of this ellipse. So the major part of the ellipse becomes the one which is centered at the origin. So it becomes as if you're just dealing with this piece. But for an ellipse, you expect that it then implies that you can position one directrix this side and the other directrix can be positioned the other side. Because for an ellipse, it implies that you can have one piece that looks like a parabola this side, and you can also have another piece this side that also comes out as if it is a parabola. So it gets to have two directrix, one this side and one the other side. Again, K is the distance from this point all the way up to where the directrix is going to be. So that is how it's going to come out there. Well, even if you're dealing with a hyperbola, you can still use the same notion. You know, to say a hyperbola is going to have two, more like two pieces. If let's say the general one that you're looking at opens to the left, or the main one opens to, I'll just use main one to mean the one which is centered at the origin. So if the main one opens to the left, like this, we know to say for the one that opens to the left, we saw how its equation will come out. If this is indeed a hyperbola, we know to say that then it must have its counterpart. How will its counterpart be oriented? We know to say it's like these are facing away from each other, unlike an ellipse where it's like they are literally like this. So it implies that the other one, for us to get this, it implies that the other one has to be the other side, but just has to face the other side. So this is basically what you're going to have here for the second piece. Now, if this is a hyperbola, it implies that you're going to have a directrix somewhere here and a directrix somewhere this side. The center for this hyperbola will have to be somewhere between those 2 points. The distance K, or K here, will have to be the distance from the focus here, coming all the way up to where this directrix is. So basically, this is how it is going to go. And of course, you know to say when sketching a hyperbola, don't forget that you always use those asymptotes, and they always go like this. We saw how we sketched them last time when we were looking, which was, yeah, in the previous class. Okay, now a lot of lines without really showing what this is all about. Let's try to find an example so that perhaps we can describe this. You just want to be very careful here. Where is the major? What are we looking at? The equation I gave you was for R is equals to EK, and then we had, this was 1 plus E, and then you had cos theta. Now this was plus, and we saw that the major one was opening to the left. What if you have R is equals to EK, 1 plus, now instead of plus, you have minus, but you are still dealing with cos theta. It implies that the major one opens to the right. Again, by major, I'm just talking about the piece whose focus is at the origin, opens to the right in this case. Then we expect it to have this form. But what if it is something vertical, as in opening either up or down? Well, if let's say the piece whose major is at the origin opens upwards, as you can guess, this one now, how will it look like? Well, if the major piece opens upwards, firstly, as you saw, when it opened to the right, it turned out to be negative on the middle. So you expect R is equals to EK, and this is 1 minus E. But now, since we're in the vertical, you're now going to use sine theta here. And if it opens downwards towards the negative, then of course this will just be plus there. Let's look at an example. Find an equation for the hyperbola with eccentricity. So we have E is equals to 3 over 2, and directrix x equals to 2. So in this question, we just want to find an equation of a hyperbola whose eccentricity is E is 3 over 2, and the directrix is at x is equals to 2. So this one is actually very, very easy because we're given what the eccentricity is, and also given where the directrix is. It should be a little bit easy. So we're looking for the hyperbola here. So how will it go? So if you look at where that 2 is, it's like what we're being given here is something like this going all the way up to there. So that this is where that 2 is. Then the next thing that we want to see here is our E. What is our E telling us? Our E, we know to say our E can be related to what? To C over A. So this is telling us what C is relative to what A is. So perhaps this can actually tell us where the vertex is, where the vertex is, and where the focus is. Now, for this part, of course, if we were to just plug this into our expression, do we have anything else being given? Eccentricity 3 over 2, and directrix x is equals to 2. Notice that in this case, I know exactly what we are looking at in terms of whether it's opening up or down or to the left or to the right, because my directrix is given in terms of an equation of x. So I know it's a vertical directrix. So I know to say I am dealing with a hyperbola which opens like this. So based on that, I'll just get this, and I can say that, okay, if this is the one centered at the origin, then my directrix will have to be 2 units from this side. I can position it somewhere here so that it is 2 units from that end. Now, since this is the one that I've gone for, I can easily now just write R is equals to my E. For E, what do I have? It's 3 over 2. And then I have K. K is the distance from the focus to where the directrix is. If I center my hyperbola at the origin this side, it then implies that that value K will actually be the same as the distance from here to here, which comes to the equation of this directrix. So this is basically just the same as that x is equals to 2 they gave me. Then this will be over 1. And remember, since I've gone for the main one to open to the right, it implies that I'm going with minus here. Then I have 3 over 2. Then I have cos theta. So the equation becomes 3 over 1 minus 3 over 2. Then we have cos theta here. Any questions here?
Where did the minus come from?
Where did the minus come from? Wait. The one opening to the right here is plus here. Yeah, sorry for that. The one opening to the right is plus. To the left, I mean. The one opening to the left is positive there. That's what you meant, right?
Yes.
Okay. We can even look at, yeah?
That's the opposite.
No. The one that opens like this has R is equals to EK, and then 1 plus here equals theta. Then the one that opens like this, so it will have a directrix somewhere here. The one that opens something like this is going to have EK, then minus here. Okay, look at this one. R is equals to 25. Then you have over 10 plus 10 cos theta. I think I saw this in a test paper. I think it was this exact question, if I'm not mistaken. So the concept here is that if you compare this, the question here, of course, is find the directrix for the parabola. So here they're saying this is the parabola that you're dealing with. So how does it work? To find the directrix here, of course, you just want to find what k is. That will tell you where the directrix is. And again, this is centered at the origin, or the focus is at the origin. So how does it work here? Well, in the general expression, you have R is equals to EK, and then this is 1 minus, not minus, plus, because this is facing to the right. I'm basically just following what that is. Then this is E, and then you have cos theta. What do you pick from this? The first term in the denominator is a 1. It must be a 1. Everywhere else, we can have numbers because they are controlled by E and K. But the first term here, which is a constant, must be a 1. So when I compare this with that, what I have there, that term must be 1. The only way to make that a 1, I have to factor out that 10. So my R becomes, in the numerator, I have 25. So in the denominator, I'll pull out 10. I'll remain with 1 plus. Second part becomes 1 as well. That will just be cos theta. Now the 10 cannot just remain hanging here. I'll divide it into my numerator so that R becomes 2.5 over 1 plus cos theta. Now, I should have an E here. In the original expression, we have E here. But when I look at this, the coefficient of cos is a 1. So this tells us that the eccentricity is just 1. Then the next thing that we see here is this part here, the top part. The top part is controlled by E and K. But we've seen that E is 1. What does that mean? It means that K is equals to 2.5. What is our conclusion? Our directrix, which is what the question wanted, is actually just going to be the line, since this is in the x-axis, x is equals to 2.5. Any questions there? Okay, something for you guys to try. Try this. So what I want you to find is find the eccentricity. Then after finding the eccentricity, identify the conic section. And after that, give the equation of the directrix and sketch it. And what are you going to have here? So this is R is equals to, the first one is 12. Now you have 2 plus 4 sine theta. And the second one is going to be R is equals to 10 over 3 minus 2, let's say sine theta as well. So when these questions come in the test or exam, this is how they bring them. Find the eccentricity, identify the conic section, give the equation of the directrix, and sketch the conic section. So this is what I'll leave you guys to try out. Okay, so any questions up to this point?